Hi, Karen. Welcome to the podcast on Everyday Metallurgy.
Hi, Peter. Welcome. And many thanks for the invitation to contribute to this podcast.
Yeah.
It's a pleasure.
And Karen, you are one of the big cannons here in Denmark. You're the chairman of the Danish Metallurgical Society. So I'm very honored that you accepted my invitation to participate here in the podcast. But first, can you give an introduction to yourself, your background, educational background, and I'm always very curious to learn about how people got into metallurgy, because some are born into it as a family addiction. Others, it's like in the mid-20s, it appears for them to be the path of life. But what is your history?
Well, first of all, thank you very much for inviting me. It's indeed a pleasure to talk in the podcast. And I think in particular, now you mentioned it yourself as chair of the Danish Metallurgical Society. It is a pleasure because DMS is metallurgy at its best, as it is, combining the network between academy and industry and providing a possibility to really talk about metallurgy. So that's what we do with DMS. And by the way, if there are some of you outside listening, just join DMS if you want. But back to the podcast. You asked for my journey towards metallurgy, and that's in fact, it started quite early because I actually was inspired by my father, who has a rather similar background. He had a completely different journey for himself, but he inspired me actually when I was a child. And that sounds often like a little bit a kind of, fluffy story, because when I read applications from students, for example, and they start, since I was a child, I knew that I wanted to go this and this way. Actually, for me, it's true. And the point is that he inspired me with a kind of, let's say, a running gag that was a running gag at home, because he asked me, what is going to happen if you sharpen a knife, or if you sharpen, for example, a knife? Mm-hmm. And then he not only asked me that, but he also explained it. And he did that actually without using terminologies like dislocations or plastic deformation, which in fact it is. Mm-hmm. But he explained me something about the internal structure of metals. So that was fascinating immediately. Yeah. And then we have been invited during school with my school class to his workplace, and there it was about materials characterization. And we got the possibility to see a scanning electron microscope. And in that scanning electron microscope, I mean, they had put some samples in, probably also metallic samples, but they actually, honestly, I forgot again. But what they also had in was a fly. And we saw tiny small things on that little insect, and that fascinated me. So just the possibility to enhance or to resolve all these small details. And that's, finally, together with the internal structure of metals, that at least raised my curiosity, were the starting point to decide for an education, which at that time actually was called material science, with the specialization in development of metallic materials. So it was very much straightforward. But anyway, not without a lot of, sudden side accidents or sudden inspirations for sudden things that actually happened during my start of the journey. And maybe even longer, or still a little bit history about that, because I started in the east part of Germany, because I come from Germany and from the old GDR. And at that time, one had to have a practical year before being allowed to study at least that particular subject. Okay. And that was a great experience.
Yeah.
Because I was employed in a company where I got the chance to go through different divisions and actually learned a lot about the daily life with or within metallurgy. And after that year was over, then I started my education. And after even more, a year was over, there came one of these sudden accidents, or very, very pleasant accidents, you can say, because the war came down. And that was at the point where I, of course, continued my education as it was planned before. But that was, on the other hand, I would say nowadays I have been at the right time, at the right place. Because it was a lot of possibility for economical support to the university I was, which was very, very much dedicated in surface engineering and materials characterization beforehand. But we got a lot of money to the university, and I was in the right age, you can say, to use that.
Yeah.
So with fantastic equipment and with the possibility to make a PhD afterwards, I stayed at the university. And well, that was the starting point for getting into surface technology, namely for metallic materials.
Yeah. And what university was it?
That was a university in Saxony in Germany, in the eastern part of Germany, near Dresden. It's a small university called TU Bergakademie Freiberg. And they have been extremely ambitious and dedicated really to materials characterization, in particular X-ray diffraction. And that's still exactly what I'm doing nowadays also. And at that time, I started doing surface engineering for physical vapor deposited surfaces. So it was steel deposited with a PVD layer. And I got the chance to investigate those with that very, very dedicated equipment. And then after 3 years of PhD, I went now to the western part of Germany, to Bremen, and I worked there in nowadays it's called IWT Bremen Leibniz Institute. It's one of the Leibniz institutes. And I started working there, or actually I continued working there about surface engineering still. And now it was not PVD coatings any longer, but it was CVD coatings. So I went to the chemical vapor deposited surfaces. And again, it was materials characterization and heat treatment of these surfaces. Yeah. And well, finally, after a bit more than 3 years, I went to Denmark. And since that, meanwhile, this year it becomes 24 years, I'm at DTU. Yeah. And there again continued with surface engineering, but now not any longer with any vapor deposited layers, but with electroplating. And of course, lots of teaching obligations for different basic material science, metals technology, and also surface engineering, and also actually materials characterization. So if you want, it was a rather straightforward way, but with lots of, sudden and good things on the way to here.
Yeah, yeah. I also studied at DTU, and I ended just before you came there. But you might recognize this one.
We still use it not in this book, but we still use one of these old books for one of our classes.
Newest I have.
Yeah, well, but there's Yeah, but it all goes back to also some tradition of DTU, of course, within electroplating. Yeah.
Yeah. Yes, and thank you very much for the introduction. You build a bridge to the technical theme that we would like to take up here on electroplating. And I would like to dig a little deeper into what is electroplating, how does it work, and where do we see that on our everyday basis? Is it only hidden in industry and in space, or is it also in my kitchen or in my car?
Well, Actually, it's everywhere. And in that sense, indeed, electroplating fits very good to a podcast called Daily Life with Metallurgy, because that is a daily life, and not only for those who are dealing with it, but I think also for everyone. Because indeed, if you look around yourself, I mean, not what I see right now, I'm not sure what the material is behind you in the bookshelf, but there are lots of examples that are not possible to imagine without electroplating. And that is, of course, for many different purposes. It could be just for decorative purposes. Sometimes, as I used to say to students, actually, it also may be for partly a little bit of cheating, if you want to call it like this. Because if you have something that is a very cheap base metal, then you can pop that up quite a lot by just plating onto it. And then it looks can look very much nice and shiny and bright and somehow more expensive than, in fact, it was originally.
Yeah.
So it's, of course, a very meaningful and widely used method for industry, but as much it is for everyday life, at your home, in your car, in your bicycle, everywhere.
Yeah, I remember my father, he was also a metallurgist, and on a business trip, he bought some jewelry in gold to my mom. It was very odd cheap. And then when he came home, he took it to the laboratory. He put it into the SEM, and it showed, yeah, it is gold. But then he made density measurement, and then density was around 10. And gold, I think, has a density of 19.3.
19 something, yeah.
Yeah, so yeah, that was a reason why it was cheap.
Well, but on the other hand, actually, that's a good point, because it looks like gold, and indeed, of course, it depends a lot how you prepare the surface, but it looks like gold. But it could have a very tiny thin gold layer on top, but also it could be done with whatever kind of different surface engineering technology, so that it only looks like gold, but indeed has properties that are, in fact, for those kind of jewelry, maybe for watch cases or things that also are mechanically attacked or risk for mechanical damage, which actually could be much more worse than gold, because it's harder, it's more wear resistant. So it depends what it is, but indeed that also is a kind of cheating a surface, looking like something else than it actually is.
Yeah.
Do you know what that example was from your father?
I think it was nickel.
Looking like gold?
No, it was nickel that was coated with gold.
Okay, so it is a very thin, but in fact real gold. But on the other hand, there are lots of other technologies that end up being or looking really like gold, but are much more hard and wear resistant, and also just a small 5 micrometer thick surface layer.
Yeah.
But that is not with electroplating. Electroplating would be gold.
Yeah. But if we take one step back to what is electroplating, how does it work, and what are you really doing when you electroplate? Can you describe a little of that?
Well, I think actually one of the advantages of electroplating that it is in principle, and I say on purpose, in principle, it is straightforward and simple. And as I used to say to my students, you can in fact do that at home, because the only thing you need is a liquid that contains, that often is on a water basis, that contains, for example, a salt that provides ions. And then you put, so it is an electrically conducting liquid. And then you put 2 electrodes in, an anode and a cathode. The cathode is your workpiece, or the thing you want to deposit. And then you get an oxidation on the anode side and a reduction on the cathode side, and that grows as a function of time a layer of your material, depending on what kind of ions and what kind of electrolyte you have, onto your substrate. So it is in principle rather straightforward, and I think also that is why it is used extensively. But on the other hand, it is so straightforward, let's say, only if you just want to end up in something that looks nice or in something that just is for decorative purpose, let's say. If you are aiming at what also lots of electroplatings are used for, if you end up in something or wish to end up in something that has specific properties and that require actually that you engineer the coating while it grows, then things are much more complex because then it is not just about putting something, a new material on the surface, but then it really is tailoring, or better to say engineering, how these coatings are growing. But all of that is, from the experiment itself, rather straightforward, but requires a lot of knowledge about the details.
So in principle, all metals could be deposited, or even also salts.
Well, there are a wide variety of metals that can be deposited. Not all of them can. Some of them can only if they are together with others. But that what made electroplating, I think, most famous. That is where it started with. That was nickel, very, very old. So this is one of the first that at all became plated. That also is copper. And the importance of copper has been quite huge in the middle of the 90s or something like that, where copper actually replaced aluminium-based materials or aluminium for interconnects, and where also at the same time the interconnects became smaller and smaller in size or in dimension. And they are also the changeover from the original PVD-based method for making those interconnects change to electroplating. So this became very, very popular for copper, nickel, for micro electromechanical systems, for example, also in small dimensions. Other things like zinc, silver, gold, you named it. Is very popular as well. There has been a time where chromium has been very popular, and at least for the hard chrome platings, and that still is one of the very big issues on the market for, in particular, having wear and particularly wear resistant and particularly hard coatings. But there are a lot of metals platable, and in general, it holds the more simple the electrolyte composition is, the easier it is to control, because there are a lot of, let's say, byproducts or side reactions that are occurring in the electrolyte that potentially can produce some chemical species that also potentially become implanted or incorporated in the growing coating. And that could make then that it is less easy to control it, or less easy to end up in the exact requested chemical composition of the coating and therefore the properties. But there's a wide possibility, both with respect to what can be plated, but also with respect to onto which substrates, onto which materials you can plate on. And I think that makes electroplating such a enormous manifold technology to whatever purpose you want plated.
Yeah. Can you also make kind of multi-layers, so make a mix of, you have both copper ions and nickel ions, and then can you separate it, controlling your voltage?
Well, I think during plating, not really. But what you can do, of course, is to go from one bus to the next, and a multi-layer, if you named it like this, that also often is used in order to adapt, for example, stresses that arise at the starting point where your coating, usually of different kind of material compared with your substrate, starts to grow. And in order to adapt these stresses or keep them low, you can, among others, put such a buffer layer in between that's, let's say, step by step goes towards the new chemical composition. But if you really want to make a multi-layer, then you go to different bases, and instead of doing that from one and the same.
Yeah.
But of course, if you put different species into the electrolyte, then you can plate alloys. But this is clearly the point. The more complex the bus is, the more difficult the plating becomes, or better to say, the more challenging, at least, it is to control and, in fact, also to maintain the bus.
Yeah. I also know that for separation usage, both nickel and cobalt, when you buy that in raw amounts, you can get it in high purity by electro depositioning, because then you separate it from impurities.
Yeah, well, that with high purity from electro deposition, that depends always, because electro deposition is one of these technologies where people used to say, and I must say, when I started with it, I may have belonged to that fraction of people saying, well, you never know what comes out of a bus because you never know what's really in it. And therefore, quite often, electroplated coatings have a little bit the rumor, let's say, that there may be whatever included, because there may have occurred a side reaction in the bus. And sometimes even people say, well, if you deposit on a Monday, you get a different result than if you do it on a Friday. This is not true. But these are some of those rumors, let's say, where people tend to say, well, there is a lot of stuff in, like, for example, also sulfur, and you never know where in the coating that finally ends up. And of course, even if it is a very small amount, it means something for the coating, not only for the growth of it, but finally for the properties. And may it, for example, if it is along the grain boundaries, then it will pin these grain boundaries, and that means a lot for a thermal evolution of a coating that typically will occur, because they are in highly non-equilibrium state when they are deposited. But if there is something situated on the grain boundaries, then this means a lot for the stability of the coating. So how pure it really is, it's at least quite a lot of those elements that also are quite difficult to quantitatively detect and to confirm whether or not they are in.
Yeah, I think often when you dig raw materials out of the ground, cobalt and nickel, they are brother sister, so they come together. So that's the way of separating them from each other. Yeah.
I'm not.
No. But you also said that this chromium is a problem, because the chromium is deposited from a chromium 6, a hexavalent bath that is known to be strongly cancerogenic. So where do we use that, and what should we do? Do we have a substitute?
Well, this is maybe at the moment, or it's not only at the moment, actually, since many years already. I think that goes back to 2013 or so, where indeed hexavalent chromium has been identified as one of the substances of concern. Since that time, it really is the biggest challenge maybe for electroplating to find an alternative. Because what it means to be identified as a substance of concern, or actually of high concern, because it is dangerous for human health and for environment, that means that people are not allowed to continue to use it. But on the other hand, it is the absolutely necessary ingredients in order to electroplate hard chrome. And hard chrome has been, and maybe still in some, or not maybe, definitely in some branches still is, one of the biggest markets within hard and wear resistant coatings. So from the point on where it came, I think, as I said, I think it's 2013, something like that, where it came on the list of substances of concern. It started to be needed to find an alternative, but this alternative still is not available. And that means, of course, we are, or everybody actually is a little bit in a kind of dilemma, because on the one hand side, we know that it is not good to continue to use it. And on the other hand, it actually is not even allowed to continue to use it. So companies who still want to use, because their products rely on hard chrome, they have to apply for a certain confirmation from the European Union in order to continue the use. Okay. And of course, this acceptance is given only in the case where an alternative is really missing. So what to do? Then they get the allowance to continue working with it, despite knowing that it's not a good thing to do. And therefore, there is clearly a very high focus on finding an alternative. But it is not easy, because hard chrome is one of these big players that actually can everything. And so that is, from the plating point of view, very well understood. It is used in lots of different things for everywhere where it should be a hard and a particularly very resistant surface. And to find an alternative must, at the best, I would say, must meet all these good properties that hard chrome has. But that obviously is not available. But people are looking for that since a long time, and we do as well. But that is a challenge, and still not a solved one.
Do you know if there is settled last buy date?
That has been already. That has been already in 2017. I think that was what was called the so-called sunset point or sunset date.
Yeah.
Because that was the time where, because announced in 2013 or something like that, everybody actually, you can say, they knew that that this end date will come. And in principle, one could have said, well, let's just develop something else. And then this sunset date indeed came already, but with the result that there is no alternative. And that's why still there are lots of applications to the European Union for asking for permission to continue its use. And the permission, to my knowledge, is given because there is no alternative. But there is a very, very hard need in order to find something that at least probably not is available to replace hard chrome in all its possibilities, but to replace it for some certain applications. And there are replacements for sure, but not for the most, demanding properties.
Okay. So if we dig deeper into hard chromium, what are the important properties? Is it corrosion resistant? Is it hardness? Is it wear? Is it? It's also used in hydraulic systems. So tribology. So how would you define the properties that you should copy in another material?
Actually, it's all of it. It's all of it, and that makes it so difficult, because it is clearly the hardness. There we should end up in a hardness, 800 Vickers and above. It is clearly tribology, so it is the wear resistance. It is the possibility also to be corrosion resistant and to can all of that with a long lifetime or relatively long lifetime.
Yeah. I remember that the surface, if you look at it in microscope, a lot of micro cracks. Do they play a role in the purpose, or what do they do?
They are not a problem for hard chrome, but you are right. Hard chrome is cracking. Yeah. But I myself never deposited hard chrome myself, but I I started doing the alternative or developing one of the alternatives or possible alternatives for hard chrome also based on electroplating. So
yeah.
Instead of, I would say, instead of looking still on hard chrome properties, let's try to go to something that can fulfill those requirements where hard chrome still is used, despite that it is not a good thing to do, but where we would like to replace with an alternative that is industrially possible and that is, let's say, as good as hard chrome, despite that indeed it will be difficult to meet all of the fantastic properties.
Yeah.
So that's our focus.
So Karen, what is it? What have you been playing with? What is in the soup?
Well, that started actually many years ago. That's actually started even longer ago, because it is few places on the world in the world where they did for different reasons originally back in the 90s, where they plated iron with intentionally deposited carbon. And intentionally deposited means that this time now you say you would like to have carbon in the iron coating, which now is not considered an impurity. And there are lots of others saying, well, if there is carbon in, or as we said earlier, if there is sulfur in or something else, it is an impurity. We don't want it because we can hardly control it. But in this particular case, it is an intentional co-deposition of carbon. And that is something what we have, let's say, a kind of revival has happened from the 90s, where it was used in Japan. And now we have used that and do that ourselves since some years, where the focus is on plating iron, but with intentionally co-deposited carbon that comes from citric acid. So in that point of view, it is environmentally friendly, because citric acid, I mean, that's what is everywhere without being somehow a problem.
We use that in the kitchen.
Right, yeah. You eat it.
Yes, a lot.
And actually it is something where the idea is that we would like to have actually a lot of carbon in the coatings, and that also works. So the amount of carbon we co-deposit just from putting iron sulfate and citric acid, roughly said, in the electrolyte, the amount of carbon we can co-deposit, that goes up to 0.9 weight% of carbon. And if you have a little bit the iron carbon phase diagram in mind, then we are
over-eutectic.
Exactly, yes, over-eutectic. Hyper eutectic. Eutectoide, not eutectic. Eutectoide. So it's well, now I'm teaching that, so I have to be careful. And I know that students often answer eutectic. No, it's eutectoide. But the point is, yes, we have so much carbon in that it actually is quite a lot, which is definitely much more than the only almost nothing amount of carbon that fits into iron at room temperature. And that, of course, immediately, based on just the chemical composition, would conclude, well, it must be something like steel, because we have iron and we have carbon. But on the other hand, of course, the amount of carbon is so much that it would need to be somewhere in the steel, namely as carbides. But they are not really necessarily carbides we can detect. And the point is that this actually has been a long journey, and a lot of detective work over years, which just recently finished with the conclusion that there are 3 different types of carbon-containing phases in the coating. One of them is a carbide, indeed, but on a nano scale. So it is not possible by means of, and we did a lot of trials, by means of materials characterization to really confirm that it is and where it is. It is, but
with X-ray neither?
No, you don't see it. And the other phase is an acetate, so it's an organic phase that, by the way, not only contains carbon, but also contains oxygen and hydrogen. And these 2 elements also are part of citric acid. So everything what you put into the electrolyte finally, at least potentially, and in our case definitely, ends up in the coating. And the third phase is something that is kind of amorphous carbon. But these all are completely different compared with what we would expect for steels, having a hypoeutectoide composition. So that means we have the chemical composition of a steel, but we do not have the kind of phases we expect from steels. And we have, on the other hand, also all these specific characteristics of electroplated coatings, namely nanocrystallinity, and actually also a very, very fine and nice and shiny surface. So our coatings also have a leveling effect. So if you start on a rather ugly surface, maybe even already a damaged surface, and you start depositing these iron carbon coatings on it, then it ends up with a very shiny and very bright surface. So there is something that smoothens it out. And normally in electroplating, you put some specific additives to the electrolyte that have this purpose, namely to level and to
pulsate the power.
No, we do not. Nope. Now we also did it with pulse plating. That doesn't change anything in the appearance, probably in the properties and in the kind of coating growth. But this happens already when we just have a constant current. And that's a point that is so fascinating, because you grow something on a surface, you see that it becomes very bright and shiny and has a leveling ability. And you know what we also tested, that you can deposit several of these coatings on top of each other. So why not to use it for repairing a surface that already has worn or has damaged? And finally, and that makes the link to hard chrome again. We also have a hardness that is after deposition already as high as 800 Vickers. So again, that remains on hardened steels. But that gets actually even higher thanks to the co-deposited carbon, oxygen, and hydrogen. Hydrogen maybe not that much, but that gets even higher in hardness when we give it a slight anneal. And there we get hardnesses much above 1000 Vickers, and that is excellent.
So then what about corrosion? Because if it's pure iron, then then you cannot see light.
You are absolutely right. Of course, corrosion is an issue, of course. And on the other hand, corrosion is only an issue if you put these coatings in dry atmospheres, or if you put them in water-containing environments or so. But corrosion is not an issue if you put them into a lubricated environment, where most of these coatings, if they are applied for wear resistance anyway, are used. So at the moment,
a hydraulic cylinder.
Something that there are lots of branches in industry that use those coatings, and of course that rely on hardness and wear resistance. But indeed, yes, at the moment, if we are speaking, if we are talking only about iron and carbon, then corrosion issues or oxidation is a point. Yes, but you can protect that by the right atmosphere or environment for your surfaces. But on the other hand, what we do at the moment, that is to further plate other alloying elements that, first of all, also contribute to an even higher hardness, but also provide as an alloy some corrosion resistance. So that is something that is ongoing, and with that we would be even free of those lubricants. But that is ongoing work, and hopefully to come.
Okay, Karen, I have two questions. I have one I do not understand. That is, how do you transfer citric acid to carbon? What happens chemically in the bath?
That goes too long for the podcast.
It's magic.
But this is as I think we should not talk about what exactly goes on in the electrolyte, because of course the carbon, the oxygen, and the hydrogen all that is part of citric acid, and all that in fact can be detected in the coating. So we do have it. But what exactly happens in the electrolyte, and what happens if the first part, or if the first chemical reaction has happened, and there are occurring some side reactions and continued processes, that is a different story.
Is it cut into smaller pieces, and do you have residuals in the bath?
That is, let's give it some time, and let's try to understand that complete. But that is something, actually, by the way, that is very typical for electroplatings. That's what exactly happens in the electrolyte is not necessarily well known. And even if you have an idea, and if you know, or if you believe how it works, it will be hardly possible to control or to predict exactly what happens with all the small species that, by the way, also in an electrolyte, in particular iron containing, that changes during time of plating, but also when it's not used, that will continue to go on and develop some further products. That is a story that ask me another time, I would say.
Yeah. Then I have another question, because typically when you have very fine nanostructure that are out of equilibrium, if you heat them up, something changes, and crystal starts to grow. So what happens if you said you were annealing it, but what temperature do you maximum accept these materials at?
Well, the annealing actually was for us a way to understand what exactly we have in the coatings. Because the annealing was something that was originally not done in order to produce a new or an even better type of coating by annealing, but it was done in order to understand what happens during annealing. And from that point, going back to what must have been there beforehand. But what definitely, you are absolutely right. If you have an electroplated coating, and that is very well known for copper, also for silver, that's part of the work I did actually in very early times when I came to DTU. They are not stable, and they will evolve partly already at room temperature, because there is a huge driving force for developing or for evolving the microstructure. And that, of course, also happens when we intentionally anneal these coatings. And what one could speculate immediately would be that the ferrite, because essentially in our coatings it is only ferrite, carbon-free, that this, because it is nanocrystalline indeed, that this will start evolving immediately when it is on temperature. But this is not the case. It actually is the ferrite itself as phase is stable up to about a temperature of roughly 250 degrees. Okay. And that is in the temperature range where all those coatings are well applied, or actually below this temperature they are well applied. Yeah. And in this particular case, we should, for evolving the coating and the microstructure and therefore associated properties, we should, of course, also think about that it's not only the ferrite, but also in our case, it is the carbon, the oxygen, and maybe the hydrogen if it not yet has left the coating already at low temperature. But they will evolve, and they will actually bring about the even higher hardness, because now with temperature, carbides and oxides are formed. And they explain why the coatings become even better in mechanical properties in terms of hardness and. But the ferrite phase itself is absolutely stable until roughly 250 degrees.
Okay, then you can actually use it.
You can use it, in fact, of course, and there, I mean, that is the best thing. That on the one hand side, you could say, if you understand what happens while the coating is evolving, then you could say, well, then I know what's going to happen, and I can plan that into the kind of application I have in mind. So it would be okay if it just evolves and you know what you are aiming at. Maybe also going back to the kind of deposition and deposit in a certain way, so that you have in mind already that this as deposited coating will finally evolve with temperature. But if things are remaining as they are after deposition and up to a certain temperature, that's even better, because there you can tailor the electroplating just by means of the process parameters and get what you want and use it. Indeed.
Yeah. Then often when you deposit, if you have a substrate with a specific structure where you have crystals, large crystals, then when you start to grow, your new layer will continue the building on the old crystals. But then you can put in between a chemical nickel layer that is amorph, so you don't have crystals to grow on. How does this material behave?
Well, actually, we use not a nickel layer, but we use an amorphous. Well, it is okay. It is kind of nickel layer. It is a nickel phosphor layer, which is amorphous when we plate it, and we use that for the development period. Because when you develop an electrolyte and try to tailor the best process parameters towards a certain microstructure, you are at that point not interested what the substrate dictates, but you are more interested what the electrolyte itself brings about. Yeah. And for that purpose, indeed, those amorphous buffer layers or intermediate layers are useful in order to understand what the electrolyte does. But you are right. Finally, if you want to deposit those coatings on, for example, steels, in fact, it would continue or supposed to continue as the underlying material dictates. That, however, on the other hand, is so far not really experimentally verified, because we get the same kind of coating growth independent of the type of substrate. So if you deposit on something else than iron or steel, then you get the same kind of coating growth as you do for construction steel or something else underneath. Yeah. But in principle, yes, and this would be an additional point to tailor the final outcome of a coating by tailoring the substrate towards a certain property.
Yeah, so if you want to use this as a repair method, you need to pre-coat the substrate with the nickel phosphorus, or can you go directly?
No. It was directly on the surface.
Okay.
For these things, it only matters that you have a good preparation of the surface before you start plating to really have a nice and nicely conducting surface to start the electroplating process on it. But there is no coating in between. No.
Okay.
And that's also the point. If you have a multi-layer, and that's what we did by interrupting the growth and then restarting the growth on the same coating as it was before, it just continues growing. And that is what you need if you have it on something else that already is a worn surface. But all that will the future show, because there are lots of details in between and lots of tricky things still to understand.
Yeah. So has this composition been tried as a hot chrome substitute in a real application, or are we still in lab?
It is. We have started the project together with a company in Belgium. And they have been convinced for the process, and they tried it. But we are at the moment developing it so that we end up in knowing what the coatings can, how they will form, what the properties are. And we have done lab-based wear testing, and at the moment actually do also those, or have planned to do also those wear resistance tests under lubricating atmospheres.
Yeah. So when do you expect that this material will be out there in real life?
Well, that is difficult to say, because it depends what you want to deposit. If your aim is to deposit something that is nice and flat and straight, then it's not a problem to actually grow a rather thick film, and we can do that reproducibly, no problem with that. But as soon as you are saying, well, my surface has a certain geometry, maybe with a lot of small gaps and a lot of small openings, and I should have a very uniform coating all the way through, there the problem starts, because that means, despite that electroplating is very dedicated to those complex geometries, this, of course, is then still a question of getting it also with uniform coating thickness everywhere. And for those more complex geometries, there still a lot of testing will be needed. So it's not possible, I would say, to say, well, it depends on the application. If you only want to have, as I said, just a plate to deposit, you can use it. But for more specific geometries or certain applications, it will still need some tailoring.
Yeah. So this electroplating in general, where will that be in 10, 20 years from now? Will it be substituted by 3D print, or?
No, definitely no. I don't think so. No. I think I think the point is that electroplating is a very old surface technology, and it has, of course, gone through a lot of history, a lot of understanding has been obtained, and I think I'm convinced that this will survive, both because it is very well possible to control it. And when I started earlier to say here in the podcast to say, well, there is a little bit of kind of, well, people do not really know what's going on in an electrolyte, and sometimes there are rumors of like alchemy or this kind. This is just indicating that electroplating is complex but possible to manage. So it's clearly a challenge, but it's not something that will die out or so. And I think where it has the biggest potential for the future, that is that it is cheap. It is cheap. It is industrially feasible. It is already for lots of different applications used in industry. And very important, actually, most of the platings happen at a low temperature. And that, of course, makes it particularly relevant compared with other methods that require some temperature. Both for the kind of substrates you can use, but also for, well, just saving energy and all that.
Yes.
But of course, the future will, even more than nowadays, be determined on those environmentally friendly plating. And that's the kind of rumors that sometimes electroplating maybe still has, but that is possible to handle. Look at our example, just the citric acid.
Yeah.
So it will survive, and it will not be replaced, I'm pretty sure.
Yeah. So how is the outlook in the future with people working with the development of electroplating? Are there new coming in, or are they all turning gray hair and then disappear?
Well, I think it is, and I can definitely at least see that also among the students, that it is a method that is very, very requested, let's say. And maybe also because it is so simple, and you actually can see, if you look through an electrolyte, you can see how things are growing. I can see that for students, that is fascinating. And I think also that definitely is something that people are aware of, and that, well, will remain. And that may hopefully also attract a lot of people who are interested, and I'm sure they are. But of course, interested in the method also would mean to be interested in a kind of development process on the example of iron carbon coatings, for example, because of course this development is for something that is potentially useful for among others, a replacement. There may be many other applications also. But that is a time-consuming process, and that, of course, is something that involves a lot of development work, in particular for complex geometries. And there are also those who want to use it should be a bit patient and willing to contribute, so that this is something that can continue in the development and at best in a, let's say, on a real relevant and practical need and example for a replacement, for example, for hard chrome.
Yeah.
But I hope.
Yeah. So if a young boy or girl listens to this and would like to follow a path in electroplating, then I know now we have DTU with you running it. And the Freiberg, are they still in it, or? I
did not electroplating there. I did not do electroplating there. I did the PVD platings there. So they are big in surface technology. But electroplating, that's what we do at DTU. My original background was wider in surface engineering than what I do at the moment. But yes, of course, if somebody is interested, then very welcome for having a look at it. And I think in particular for attracting young people, it is one of these fascinating things because, as I said, you see what's going on. And that's a different thing than if you have a big chamber, which is a closed something, and you put a sample in and press a button, and after that you get it out and have the result. With electroplating, you can follow while it's plating. And that's really fascinating. And it would not be the first time that students standing in front of an electrolyte and saying, oh my God, I'm producing something. So that's really there where you see metallurgy at its best, I would say.
Yeah.
Yeah.
Yeah. Thank you, Karen. I am out of questions, and I think we're also out of time. I really enjoyed it, and I learned something new. It was very new for me that you could mix in organics.
Well, they are all usually they are all in the electrolyte because you add them for a certain purpose. In our case, just we don't add them for a certain purpose more than just providing the carbon source.
Yeah.
And they do a lot of other things that are a favor for the final coatings.
Yeah. So they are also the agent for securing the flatness.
Obviously, yes, because there's nothing else in it. Yeah.
Yeah.
Yes.
Yeah. So, thank you very much.
Thanks to you.
I am looking forward to seeing you again. Enjoy the day at the bath. Yeah. See you.
Thank you very much. Bye-bye.
Bye.